Good afternoon, everybody. We're Team 6, and our product is a demonstration kit for electrodynamic screens, also known as SolarClean. I'm Ryan, that's Courtney, Paul, Bill, and Kevin. So our product is an educational tool or a product marketing tool to showcase a technology. I'm going to step into what the technology is first so you can understand it. It's an electrodynamic screen. It is a thin, transparent film that we place on top of a solar panel. Now this film has electrodes running through it. When it's activated by multi-phase high voltage wave, it's able to move sand and dust particles off of the panel. Now, why is that important? Deserts. Deserts are nearly ideal locations for placing large solar farms. However, due to losses from dust deposition, as well as the tedium and expense of maintaining those systems, they're not exactly attractive projects to invest in. The EDS aims to alleviate those issues and make such projects feasible. Now what our product is the product marketing tool to show people that this actually works and works well, and you can actually place systems in the desert. We've made this for Professor Mazumder, who performs research here on this technology at the Here's the three segments of our project. We have a top compartment with the photovoltaic cell, the EDS mounted on it, and the dust. We have a bottom compartment with all of our electronics, which we'll cover in a bit, and our user interface is in the form of an Android application. A brief technical overview. We have a power supply with three-phase output. It's high voltage square waves, and we have variable parameters for it. We have a 12-volt lithium-ion battery to power all of our voltage needs. We have a TI microprocessor that interfaces with our entire system, and we have Bluetooth communication from the demonstration kit to an Android app. Now, my part was to design the voltage and current sensors to keep track of the solar panel output. This is important so we can see that once we deposit dust, the output decreases. Once we activate the device, dust moves off and the performance increases again. I also researched and selected our MSP430F5438A. It met all of our requirements. It has a lot of ADCs and GPIO pins. I had designed and adapted the circuitry around it to fit on our PCB. And I also programmed the ADC modules to read data from our sensors.
So I worked on a couple different software applications for this project. I wrote the entirety of the Android application, and so I did all the Bluetooth functionality there. And I also had a real-time display that updates once every 2 seconds. And this displays the last 6 voltage and current readings from the solar panels in the demonstration kit. And then I had a user interface that allows the user to control various aspects of the power supply that drives the EDS. And then I also worked with the microcontroller in the kit, and we had no on-chip Bluetooth support, so this involved interfacing with an external Bluetooth peripheral. I did that, and then I also integrated a couple of different inner routines that other group members wrote into the final microcontroller code. And then with the housing as well, I designed that, I did material selection, made the CAD files, and then oversaw the actual construction of that as well.
My first main role for the ECEDay SolarClean is the high voltage power supply, which drives the electrodes to move the dust. I led the design of the circuitry. Working off a previous model, I designed all the new circuitry that boosted the performance and efficiency of the new power supply, including the new circuitry that is used to create variable parameters such as the variable frequency, duty cycle, and voltage, which I wrote the microcontroller code for to make it completely digital so that we can interface with the Bluetooth and we can control the power supply parameters through that. And another main role I had was to take all the team schematics, and I designed the entirety of the PCB, which included all the part placement and routing. And my last main role was the electrodynamic screen. I just oversaw the fabrication, which was done by the Applied Electromagnetics lab. And I routed the interconnections and made the wires that would connect to the power supply. I also assisted with the housing, just some small parts like a 3D part in the bottom and the sealing and encapsulation of the EDS onto the PV cell and onto the housing so that dust wouldn't get down into the electronics and blow things up.
So I helped Bill out with the high voltage power supply. It's a 1.2 kilovolt power supply, so it's very dangerous to work on it alone. So I helped him with the testing of it, and I assisted with some of the development. I created the schematic from the old model so that we could see what could be taken out and so that we could also put it into the PCB. I was in charge of making the power supply more efficient, cost-wise and energy-wise. Cost-wise, there's a big boosting component that costs about $90, and I designed a new boosting circuitry that we didn't include due to time, but it has been improved upon by other students and will be used soon. I also reduced the power consumption of the device by about 75%, and removing other components from the old supply, we were able to reduce the cost.
And finally, I was involved with mostly the charging system, the actual solar cell itself, and the battery. So I selected and characterized the solar panels outside. So we're using 2 panels in series with an open circuit voltage of 9 volts and a short circuit current of 310 milliamps. I also picked out the battery. So we're using a 12-volt lithium-ion battery. It has a capacity of 2.6 amp hours. So with all of our stuff powered at the same time, it can run for over 6 hours. I also designed the regulator circuits for delivering power to the entire system. So we have 12 volts to 5 volts with a DC-DC converter, and then 5 volts to 3.3 volts with a linear regulator. I also oversaw most of the PCB assembly, so that was just manually soldering all of our components on there. And I also integrated the entire board into the housing with like all of our various switches and LEDs. Also, while testing the board, I also performed rework on the board as needed. We had a couple circuits that were incorrect, so I basically cut the traces and soldered on new jumpers so that I could get all of that working. And now here's the 60-second video. We actually took it during our functional testing. Sorry, this sounds not good.
So this is the voltage sensor working first with, we have a little solar lamp, and we read about 13 or 14 volts on the multimeter, and we're reading the same value on our device. Then here we're testing our square wave outputs. In our actual demo kit, you don't really see this part, but here we're changing the duty cycle. We play around with the voltage level and the frequency of the output. You will never see that because it's an enclosed box, but to show you that we actually do have that functionality. See there, the voltage level is changing. Up and down. There's the frequency changing to higher frequency. All of this being controlled by the application on the Android. And then coup de grace, it's moving dust. We had our customer installation on Friday. Professor Mazumdar was very happy with our product. He said it met all the requirements, and they look forward to actually using this and building upon it. And yeah, it's lightweight and portable. It's a very, very simple interface, really easy to use, at least we think so. We clearly show that the EDS works to the best of our ability, and we have the adjustable power supply for further testing from the lab. We also thoroughly enjoyed making this product because it promotes the development of solar energy in desert climates, which can hopefully is a step towards a greener and more sustainable energy future. Thank you.
So in the video, removing the dust, you couldn't really see how it was being removed. So did it fall through something, or does it get swiped off? How did the dust get removed?
So the EDS is a 3-phase set array of electrodes that are all lined up in parallel in interchanging phases. So pulsating with the power supply, which creates the 3-phase high voltage wave, the square wave, will create a traveling electromagnetic wave, which functionalizes the dust to move off.
Yeah, the dust and sand, when it makes contact with the surface of the EDS, in a phenomena that is still being studied, they become slightly charged. You have a point charge in a moving field. Right hand rule, move stuff off.
You mentioned making enclosures for both compartments. I see one compartment, I guess. What is the second compartment?
Sorry, yeah, so We have the clear part on the top, which we consider to be the top compartment, the part which everybody sees, and then we have the bottom compartment, which is the opaque section, which we have open in the second image. So those there.
Yeah, they're
Two
stacked on
compartments.
top of each other.
You may want to say how the dust is deposited in the first place.
So we're just using a straight up method of taking the lid off and putting dust on, however method you want, because depositing dust is not a very easy task, especially if you try to seal the box, etc. But another issue that we decided to not face is that the EDS degrades over time and needs to be cleaned regularly, etc. Also, the EDS is not perfect as of yet, and also we stuck 4 of them together for this demo. Usually you'd want one that encompasses the entire surface area of the solar panel. So here, since we stuck 4 together, if you see in the middle, you see that cross in the middle of the device, that would just accumulate dust on top and look really ugly. So by having a lid, just depositing on manually, we can just also wipe, clean the slate, and rinse and repeat. Also leaves it accessible so that we can replace the EDS in the future.
How does the duty cycle and voltage level affect the performance of the dust?
So we implemented the ability to change those so that the lab can actually test how changing that affects the output. We as a group do not have all the different types of dusts on hand to play with and see how the different duty cycle, voltage level, etc. affect them, but now the lab will have that ability to do so.
How would this work on a large scale? So either a larger solar panel or using it on multiple solar panels, like in a solar panel farm.
So ideally, you would have one of these per solar panel, but at the moment, this is still a technology in research. It's still in the lab, so we haven't extrapolated it to that just yet. Bill, do you want to add anything to that, or?
We haven't done large-scale production of large surface area EDSs as of yet, because right now we're still testing on making sure they are environmental proof and they would withstand the test of time, etc. Encapsulation methods and resistance to weathering is also still an issue, but we've proved that the concept works and that it's like a plea for help. We're showing that this technology works and could save the solar energy crisis, in which solar energy is too expensive to use. If we could get that and put more money into this research using this device, hopefully we can get money to make this large scale and actually have an effect in the future.
All right, thank you.
Thank you.